All right, so I'm going to talk to you guys about some instrumentation stories. Some of you guys have talked to me. These are all things that I have done in the past. I have worked on a lot of things. On the left there, that is an ionospheric sounding rocket. I took out some instrumentation and I made radio measurements of the plume of that rocket, which didn't work. Actually, we saw nothing. That's kind of cool though. In the middle, that is a volcano. That's Sakurajima. I was there at least twice, maybe 3 times. Sakurajima is an awesome volcano. If you guys have never heard of it, I'm not a volcanologist, but I had a ton of fun there. It erupts like every week. It's great. And sometimes it produces lightning. And on the right there, that far right picture, that's a lightning flash that happened during the GLM satellite validation campaign. And I was out taking data in that too with, actually I think the instrument that I'm going to talk about here today. But before then, we're going to have a story. So once upon a time, there was a dapper man who was taking a load of scientific enlightenment to market. So these are some pretty bad images. They're great. Speaking of AI generation stuff, I was meaning to try and update these for this year to see if they've gotten any better, but I never really quite had the time. So unfortunately, this dapper man reached the giant chasm of measurement, and he was like, what do I do now? How do I get my scientific enlightenment to market? And he looks around, and luckily, not too far away, there's a bridge going over the chasm. He's like, all right, I'm going to take the bridge. It's got a massive toll, and I have more money than sense. This bridge is going to do me great. Unfortunately, his load of scientific enlightenment is way too big for that bridge, and he gets stuck, and he never gets his scientific enlightenment to market. Well, crap. But don't worry. There was also an energetic young girl. She also had a load of scientific enlightenment, and she was also trying to take it to market. Maybe she'll make it. I'm not very optimistic. And so, as she's coming along, she reaches the gorge of measurement, and she says, I can do this. I'm going to build a bridge. I'm going to cross this gorge. And so she starts. She's building a bridge, but it takes way longer than she thinks. And she's still there to this day, building a bridge to cross the chasm of measurement. So what's the point of the story? This is, kind of this basic question of build it or buy it. And, in my parable here, neither one of them worked. And this is me saying that there's compromises with both of them. Typically, buying something is going to be quicker, but it's going to come with compromises. And building something is going to be slower and has less compromises. But you got to be kind of careful about how you handle this. Usually I'll say that if there's an off-the-shelf component that will do exactly what you want it to do or more, it works out better to just buy it than it will be to try and build something. But on occasion, almost all the time, the right option is going to be somewhere in the middle. And that's going to be the case all the time. If that first guy had just, expanded that bridge a bit, maybe he would have gotten across, for example.
You could all just become theorists.
Well, yeah, but then you wouldn't be here, would you?
Well, you have to deal with that.
Yeah, I don't like you anymore. That's not true. So I want to give you an example of something kind of going on along these lines. That's me in my crabby shirt because I'm a negative person. Young graduate student me, and I was working on a project to build an instrument. Some of you guys have talked to me about this. This was a radio measurement device to image lightning. So here's the device. The antenna here is on the left. That is what we're going to be mostly talking about. These antennas are, I made these out of cake pans. So the base of this instrument is literally a cake pan on top. Worked great. And then That equipment sends signals into this old trailer where there was a computer to record it. This is not too much different than the systems that you're working with today, except that it samples a little bit faster. So we go ahead and take a look at the system. This is what I put together. And honestly, this is a pretty good example of what I'm talking about by some of this is going to be sort of a combination of the two. Did I build this housing? Absolutely, I did. But every single component in there, all those filters, these guys are filters here, and then these components here, that, this, those are all just off-the-shelf parts. The only component that I built is this thing, which is literally just a bus with wires going across it, and this one custom circuit. Everything else is just off-the-shelf parts, put together in an interesting and meaningful way that's hopefully going to work, right? And so we deployed this system, and we set it out, and we got data. This is an example of an image of lightning that we made with this thing. I have a video of this, because it is time resolved, and we're not going to watch the whole thing, because this is 4 minutes long. But to kind of give you an idea of what this looks like, here is our lightning flash moving along. Jumping forward, you'll start to see it develop across the sky, keep going. This is about to touch the ground because this is a cloud-to-ground flash. Bang, there it goes. And then as it keeps on going, 4 minutes later, this is all one lightning flash. It's awesome. This thing was great. I was really excited about the results. We did this, we built this thing, and as a result, we ended up with a couple publications out of it. First two were in sort of standard publications, and that last one is in Nature, which is pretty cool. That was a success. So great, I'm no longer being negative, right? That's the end of the story, right? Well, no. After this, I graduated, I got my PhD, and then I moved to Japan for a postdoc. And in Japan, I was there to basically take this system and adapt it so that it could run in real time. Because when I was running this thing, one of the downsides is it took a little bit of compute to produce those images. Nominally speaking, I would spend about a week processing one lightning flash. So, about a second of data took about a week's worth of compute. Not great, but you do what you have to do, right? So the question is, how do we make a week's worth of compute go in 1 second? We're not going to go over that, but we did have to build a whole new system when we did this. And so the way this worked is we farmed that whole process out to an engineering firm in Japan. And there were some dangers in this that were, we could definitely talk about. One of them being that me, dumb American, doesn't speak Japanese. And the engineers, well, they speak a little bit of English, but it's not great. So there were definitely some language barriers. But this is what they produced for us. And this definitely looks a lot fancier than the system that I put in. You don't see any proto boards anymore. The custom circuitry they have here looks really pretty, right? And nice custom machine parts, no culinary apparatus to be seen. All of that's fantastic. And so we deployed this in Japan and on the north coast of Japan, and we got some pretty good data, actually. So this is one of those antennas. This is the guy who's funding it all. That's Zen Kawasaki. And then this is an example of some of that data that we were recording, where this green thing here is this, and that is a lightning flash coming up off a wind turbine, which is pretty cool, right? And that's kind of what we were out there to go look at. Success, everything's great, right? Well, no, not really. Up until now, did it ever work? Well, yes, it did. It worked right here. But then we took it out to Singapore, and we did the same thing on a building. And so we were trying to install this on top of a building in Singapore to do real-time detection of lightning in an area that has like 300 days of thunderstorms a year. Sounds pretty cool. Unfortunately, it never worked. We weren't really sure why. Like, the data we were getting was just trash, and I had no idea what was going on. So my solution to this was that somebody offered me a job in Maryland, and I said, yes, I'll take that. No questions asked. Wasn't quite done with it. We actually took this system out to Huntsville later on. I mentioned that there was that lightning flash that was on the front cover there. That was during this campaign. This is right after a geostationary satellite had been launched, one of the GO satellites that you guys might use for weather. Well, it also happened to have a new lightning sensor on it. That was the first GLM. And at the time, we were trying to figure out whether or not that instrument even worked. So there's a big, huge field campaign, and we took this system out. This is my graduate student at the time. That's Kuma Ami. She doesn't like photos, so she's never ever looking at the camera because usually it means that she doesn't know I'm there. And we set this thing up, and it still didn't work. And so the good news is I had a little bit of time to actually try and diagnose it, and we did eventually figure it out. So this is, the previous slide that we were looking at. Now we're going to talk about my design and how this is different than the new design I got from the engineers. And what's going on here is that this is my power supply right here, coming in from line voltage. And it's a 24-volt power supply. But these guys over here, these are the VHF amplifiers, and they're 12 volts. And so somewhere in here, I need to convert from 24 volts to 12 volts. And that's actually what this little custom circuit is doing, this guy. And it's a linear regulator. And that's hideously, hideously inefficient, right? Because we haven't really talked about linear regulators. But the way they work is that they're going to take all of the leftover voltage and they're just going to output it as heat. But these amplifiers don't actually draw that much current, so I can kind of get away with this. And the reason I want to get away with this is that I'm running a DC voltage down a really, really long wire. That is the cable going to the antenna. And we've talked about this a little bit here, but a really long cable like that is going to have a voltage drop over it. And so I'm purposely putting in way too much, so I don't have to care how long that cable is. I'll just regulate it down to where I want it on the other end. And that'll work. I'll produce some heat, but I don't need to be efficient. Who cares about efficiency? However, in the new system, they didn't do that because they were real engineers. And they said, we can't do this ridiculously inefficient method. And so instead, what they did is they had amplifiers that required a particular voltage, and they basically sent that particular voltage over the line. And so in Singapore, when we made the lines really, really long, suddenly we weren't providing enough voltage to our amplifiers, and they no longer worked. We were basically getting no signal out of the system. Our short-term solution for this was not to hack apart the fancy machine, but instead I called a friend of mine, Richard, who had cloned my machine at New Mexico Tech, where I graduated from, and produced this monstrosity here. And if we look at this thing real careful, it's bad. It's real bad. Among other things, he is right here are some attenuators, and he is sending DC voltage through those attenuators somehow. And it works, and he tested it, and we knew it worked. So we deployed this, and in fact, you can see our collinear apparatus. This is a fast antenna with a salad bowl, right? A literal salad bowl is how we do this. And then here are our cake pans hanging out in the Alabama sun, doing their thing. And this worked. We got actual good data from this. So as a short epilogue, these are my original instrument right here. And we actually got some additional publications out of it from Julia Tillis. And then actually there was one more from Richard's clone, published by a guy named Dan Jensen. Dan Jensen went on to work at Los Alamos, and he's still doing this stuff with radio interferometers. It's no longer my design. He's no longer using cake pans to do the interferometry. He has real antennas because he makes more money than I do now. Epilogue number 2 actually is pretty interesting. There was actually another clone of this system that was put together by a guy named Steve Kummer at Duke University. So here's a photograph of it. And I asked Steve about this when he said he did it. I said, I hope you made a better antenna than mine, because my antenna was really a shitty design. had all sorts of limitations. I mean, it was basically a cake pan with a piece of metal on top of it. You did a better job, right? And he said, no, I did a much worse job. These are pizza plates. But it works, right? And so he put together that system, and being a Duke University professor, I found at least 6 publications that he did with the system since then. A lot of these are really great publications too. Excellent work. And what I want you to get out of this is that spending more money on an instrument doesn't get you better science. And I don't want to throw the engineers under the bus either. There's another problem that was going on. The engineers, when they produced the system, they worked off of the specification we gave them. And they delivered a system that works. We know it works because we took it out and we deployed it and it works. The reason it stopped working is because we deviated from the specification we gave them. And so it was our fault, not necessarily the engineers. Was there some communication problems? Oh, definitely. Absolutely. But it wasn't just because the engineers were bad. I don't want to tell you, don't hire John, always do it yourself, because that's a bad plan, honestly. You should make use of John's expertise to get things done if that's what you need to do. More of it is that when you go to John, you need to be upfront about the requirements and the intended use case of the instrument that you're planning on putting together. Because if you deviate from it, he may not have tested it. Perhaps.
Will not have.
So the moral of the story is that more expensive is not better science. And maybe more importantly is that instruments work better with coloring apparatus. I think that's all I got. Yeah, that's the end.